In physical cosmology, baryogenesis is the generic term for the hypothetical physical processes that produced an asymmetry between baryons and antibaryons produced in the very early universe. The baryonic matter that remains today, following the baryonic-antibaryonic matter annihilation, makes up the universe. Baryogenesis theories employ quantum field theory and statistical physics to describe such possible mechanisms. The difference between baryogenesis theories is the description of the interactions between fundamental particles. The next step after baryogenesis is the much better understood Big Bang nucleosynthesis, during which light atomic nuclei began to form. Background: the Dirac equation, formulated by Paul Dirac around 1928 as part of the development of relativistic quantum mechanics, predicts the existence of antiparticles along with the expected solutions for the corresponding particles. Since that time, it has been verified experimentally that every known kind of particle has a corresponding antiparticle. The CPT theorem guarantees that a particle and its antiparticle have exactly the same mass and lifetime, and exactly opposite charge. Given this symmetry, it is puzzling that the universe does not have equal amounts of matter and antimatter. Indeed, there is no experimental evidence that there are any significant concentrations of antimatter in the observable universe. There are two main interpretations for this disparity. Either the universe began with a small preference for matter, or the universe was originally perfectly symmetric, but somehow a set of phenomena contributed to a small imbalance in favor of matter over time. The second point of view is preferred, although there is no clear experimental evidence indicating either of them to be the correct one. Sakharov conditions. In 1967, Andrei Sakharov proposed a set of three necessary conditions that a baryon-generating interaction must satisfy to produce matter and antimatter at different rates. These conditions were inspired by the recent discoveries of the cosmic background radiation and CP violation in the neutral kaon system. The three necessary Sakharov conditions are baryon number violation, C symmetry and CP symmetry violation, interactions out of thermal equilibrium. Baryon number violation is obviously a necessary condition to produce an excess of baryons over antibaryons, but C symmetry violation is also needed so that the interactions which produce more baryons than antibaryons will not be counterbalanced by interactions which produce more antibaryons than baryons. CP symmetry violation is similarly required because otherwise equal numbers of left-handed baryons and right-handed antibaryons would be produced, as well as equal numbers of left-handed antibaryons and right-handed baryons. Finally, the interactions must be out of thermal equilibrium, since otherwise CPT symmetry would assure compensation between processes increasing and decreasing the baryon number. Currently, there is no experimental evidence of particle interactions where the conservation of baryon number is broken perturbatively. This would appear to suggest that all observed particle reactions have equal baryon number before and after. Mathematically, the commutator of the baryon number quantum operator with the standard model Hamiltonian is 0. However, the standard model is known to violate the conservation of baryon number non-perturbatively, a global U anomaly. Baryon number violation can also result from physics beyond the standard model. The second condition, violation of CP symmetry, was discovered in 1964. Due to CPT symmetry, violation of CP symmetry demands violation of time inversion symmetry, or T symmetry, in the out-of-equilibrium decay scenario. The last condition states that the rate of a reaction which generates baryon asymmetry must be less than the rate of expansion of the universe. In this situation, the particles and their corresponding antiparticles do not achieve thermal equilibrium due to rapid expansion, decreasing the occurrence of pair annihilation. Baryogenesis within the standard model. The standard model can incorporate baryogenesis, though the amount of net baryons thus created may not be sufficient to account for the present baryon asymmetry. This issue has not yet been determined decisively. Baryogenesis within the standard model requires the electroweak symmetry breaking be a first-order phase transition, since otherwise sphalerons wipe off any baryon asymmetry that happened up to the phase transition, while later the amount of baryon non-conserving interactions is negligible. The phase transition domain wall breaks the p symmetry spontaneously, allowing for CP symmetry violating interactions to create C asymmetry on both its sides. Quarks tend to accumulate on the broken phase side of the domain wall, while antiquarks tend to accumulate on its unbroken phase side. This happens as follows. Due to CP symmetry violating electroweak interactions, some amplitudes involving quarks are not equal to the corresponding amplitudes involving antiquarks, but rather have opposite phase. Since time reversal takes an amplitude to its complex conjugate, CPT symmetry is conserved. Though some of their amplitudes have opposite phases, both quarks and antiquarks have positive energy, and hence acquire the same phase as they move in space-time. This phase also depends on their mass, which is identical but depends both on flavor and on the Higgs VV, which changes along the domain wall. Thus certain sums of amplitudes for quarks have different absolute values compared to those of antiquarks. In all, quarks and antiquarks may have different reflection and transmission probabilities through the domain wall, and it turns out that more quarks coming from the unbroken phase are transmitted compared to antiquarks. Thus there is a net baryonic flux through the domain wall. Due to sphaleron transitions, which are abundant in the unbroken phase, the net antibaryonic content of the unbroken phase is wiped off. However, sphalerons are rare enough in the broken phase as not to wipe off the excess of baryons there. In total, there is net creation of baryons. In this scenario, non-perturbative electroweak interactions are responsible for the B violation. The perturbative electroweak Lagrangian is responsible for the CP violation, and the domain wall is responsible for the lack of thermal equilibrium. Together with the CP violation, it also creates a C violation in each of its sides. Matter content in the universe. Baryon asymmetry parameter. The challenges to the physics theories are then to explain how to produce this preference of matter over antimatter, and also the magnitude of this asymmetry. An important quantifier is the asymmetry parameter. This quantity relates the overall number density difference between baryons and antibaryons and the number density of cosmic background radiation, photons and gamma. According to the Big Bang model, matter decoupled from the cosmic background radiation at a temperature of roughly 700330000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Kelvin, corresponding to an average kinetic energy of 70033000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 0.3 electron volts. After the decoupling, the total number of CBr photons remains constant. Therefore, due to space-time expansion, the photon density decreases. The photon density at equilibrium temperature T per cubic centimeter is given by, with Kb as the Boltzmann constant, h as the Planck constant divided by 2 pi and c as the speed of light in vacuum. At the current CBr photon temperature of 70027250000000002.725 K, this corresponds to a photon density N gamma of around 411 CBr photons per cubic centimeter. Therefore, the asymmetry parameter eta, as defined above, is not the good parameter. Instead, the preferred asymmetry parameter uses the entropy density S, because the entropy density of the universe remained reasonably constant throughout most of its evolution. The entropy density is with P and ρ as the pressure and density from the energy density tensor T mu nu, and G** as the effective number of degrees of freedom for massless particles at temperature T. For bosons and fermions with G and Gj degrees of freedom at temperatures T and Tj respectively. At the present era, S equals 7000704000000000007.04 n gamma.